Hi, it's Paul Bamberg with the last of the Math156 Bootstrap scripts. This one was a real challenge. I took the example from the textbook on page 123, example 5.7, and with some effort managed to reconstruct all the numbers and graphs that you find for this example. So let's get going. Here's the scenario. We have only a very small amount of information. Namely, out of 3,338 men with high blood pressure, 55 of them died over some period of time, and the rest lived. And out of 2,676 men with low blood pressure, only 21 of them died. And the question is this so-called relative risk significant? It does look as though in the high blood pressure group a greater fraction died than in the low blood pressure group, but could that have just arisen by chance? So we're going to approach this using a bootstrap. First, I'm going to create a data frame called BP, and BP is going to be the blood pressure vector that has 3,338 high entries followed by 2,676 low entries. And then the outcome for the high group, we need 53 dies followed by 3,283 lives, and a similar pair of numbers for the low one. And now we can put these together into a fabricated data frame that we'll call cardio. If we look at this, you'll see that in each row we just have two pieces of information. Was the blood pressure high or low? Did the man die or did he live? This might prove useful somewhere else, so I've saved it. Now this is large, but it's not really a population. It's a sample, isn't it? So what we can do is bootstrap from it. Bootstrapping basically means taking a sample and treating it as if it were truly a population. First, let's compute what I guess is technically called the relative risk from the raw data. I'll compute the number of high blood pressure men and the number of low, and then I will compute the proportion of deaths in the high blood pressure group. That's 0.016 deaths. I'll compute the proportion in the low group. That's 0.007 deaths. And the relative risk is the risk in the high group divided by the risk in the low group. This number is slightly different from the one in the textbook. I think that's just a matter of round off. Now we're going to try to bootstrap this. We will do this first by splitting up the data into a high blood pressure sample and a low blood pressure sample. And let's check before doing resampling 10,000 times that it's really working. What I'm planning to do is to sample from the high blood pressure group, and I will get a bunch of lives and dies, and it correctly says the levels I find in this vector are die and live. Something similar for the low blood pressure group. And now I can compute the risk of death from the high blood pressure sample, the risk from the low blood pressure sample, and take the ratio, which is the statistic that I'm planning to bootstrap. So you can see what I've done. What I've done is to say, let's treat this as a population, and suppose that we had a random selection from this population. What fraction of deaths would we get in each group, and what's the ratio? We can do this over and over and over again. And I've got to say, you can also do this using R binom rather than resampling techniques. So in this case, there is actually a more straightforward way of getting the result. Okay, so now we'll do our 10,000 bootstraps. and we'll make a vector of ratios, a vector of proportions who died in the high group and in the low group. So here goes. We sample from the high blood pressure group. We sample from the low blood pressure group. Notice we're doing this with replacement. We will calculate the proportion of deaths in the high blood pressure group, the proportion in the low blood pressure group, and the ratio of the two. And then we will plot a histogram of the ratio. This plot closely resembles figure 5.16 in the textbook. And you can see that we get relative risks that are always greater than 1, but can run up into the 4 or 5 range. Let's look at the mean. That's a little more than 2. And let's also look at the original relative risk we calculated. Hey, shouldn't those be the same? No, they won't be. Why? Because when you take ratios, you're introducing bias. The mean of the ratio is generally greater than the ratio of the means, and we can calculate that bias. It's about 0.11. From our bootstrap distribution, we can get the standard deviation of this ratio, which is about 0.6. And so this bias is significant, but it's still small compared with the variability of the ratios. Now we'll calculate a confidence interval. Let's do it the simple way. Compute the bootstrap percentile confidence interval by just taking this vector of ratios and asking for the 2.5% and 97.5% confidence intervals. We can mark those and say, look here, only 2% of the time, 2.5% of the time, did we get a relative risk that was to the left of that lower green line, and therefore the mean almost certainly is a number that's significantly greater than 1. That is, we tried simulating this by bootstrapping, and 95% of the time we were in between the green lines, and that's where the true ratio is going to lie. If we did this using a normal approximation, we'd get quite a different result. I can do this by using the mean and standard deviation of the ratios, and I plot that as magenta lines, get quite a different confidence interval. I repeat, I'm not convinced that the bootstrap confidence interval, the percentile confidence interval, is doing the correction in the right direction. Now, here's a nifty way to display this data with a scatter plot. This is going to replicate figure 5.17 in the textbook. I will set up a blank plot, and on that I will put the actual data of proportions of deaths in the two different cases. That horizontal line represents the mean proportion of deaths in the high blood pressure group. The vertical line does the same thing for the low blood pressure group. And where they intersect is the ratio that gives us the so-called relative risk. Now, on that, let's plot three things. First, the mean for the bootstrap. The slope of that is the blue line. It doesn't go through the intersection of the red line. That just means that ratio is a biased statistic. We already knew that. Here are a couple of black lines, and those mark the 2.5% and 97.5% quantiles for the bootstrap. And you can say, look, we simulated this 10,000 times, and 95% of the time the results we got lay within the interval bounded by those two sloping black lines, and therefore we're fairly sure that the true relative risk lies in between those lines, that the relative risk is represented by a line that has a slope somewhere in between the slopes of those two black lines.